Hello, everyone. Today we begin Chapter 3, Time Domain Analysis of Systems, Section 1. Solving for the response of continuous linear time-invariant systems using differential equations. We will introduce the content in 3 main parts. First, let us begin with Part 1. Time domain analysis of continuous time systems. 1. We must clarify the task of system analysis. Given a system model and an input signal, determine the system's output response. Among these, continuous time linear time-invariant (LTI) systems are the most common and most useful class of systems. The mathematical model describing a continuous time LTI system is a linear constant coefficient differential equation, starting from the system model. Studying in the time domain how the input signal changes after passing through the system is called the time domain analysis method. Next, we present the mathematical description of a continuous time linear time-invariant system. A continuous time LTI system is described by an nth order linear constant coefficient differential equation, is shown in the plot. Among these, nth order. This refers to the highest order of derivative that appears in the differential equation. In general, n is greater than m. Linear. This means that the dependent variable y of t and all of its derivatives, as well as the independent variable f of t and all of its derivatives, appear only to the first power, and there are no product terms involving these quantities. Constant coefficients. This refers to the case in a differential equation where the coefficients ai of the dependent variable y of t and its derivatives, as well as the coefficients bj of the independent variable f of t and its derivatives, are all constants. In this equation, y of t is the system response. For example, the current or voltage in an electrical circuit, also called the output signal. F of t is the excitation signal of the system. For example, a voltage source or a current source in an electrical circuit, also called the input signal. Next, we will formally begin our study of the classical time domain analysis method. To analyze the response of a signal passing through a continuous time linear time-invariant system, we can determine the system's output using the methods for solving differential equations introduced in advanced mathematics. This is known as the classical time domain analysis method. The general solution of the differential equation, which is the complete system response, consists of the homogeneous solution y sub h of t and the particular solution y sub p of t. The form of the homogeneous solution y sub h of t is determined by the characteristic roots of the homogeneous equation. The form of the particular solution y sub p of t is determined by the form of the excitation signal on the right-hand side of the equation. First, let us find the homogeneous solution. The homogeneous solution y sub h of t is the solution to the homogeneous differential equation. Its basic form is k multiplied by e to the power of st. Substituting k times e raised to the power of st into the above equation, we obtain the following expression. Factoring out k times e raised to the power of st and simplifying, we obtain this expression. Since k times e raised to the power of st is not equal to 0, the expression inside the parentheses must be equal to 0. That is, s to the power of n plus a sub n minus 1 times s to the power of n minus 1 plus a sub 0 equals 0. This equation is called the characteristic equation corresponding to the differential equation. By solving the characteristic equation, we obtain the characteristic roots Si, from which we can write the form of the homogeneous solution. The form of the homogeneous solution falls into 3 cases. when characteristic roots are distinct real roots s1, s2, sn, y sub h of t equals k1 times e raised to the power of s1t plus k2 times e raised to the power of s2t plus k n times e raised to the power of snt. When characteristic roots are equal real roots s, y sub h of t equals k1 times e raised to the power of st plus k2 times t times e raised to the power of st plus k n times t to the power of n minus 1 times e raised to the power of st. When the characteristic roots form a pair of complex conjugates, the form of the homogeneous solution y sub h of t is shown in the figure. The ki in the above expressions are undetermined coefficients, determined from the system's initial conditions. Let us review the process for determining the form of the homogeneous solution y sub h of t. 1. From the differential equation, obtain the corresponding characteristic equation. 2. Solve the characteristic equation to obtain the characteristic roots si. 3. Based on the form of the characteristic roots si, write the homogeneous solution according to the three cases. Next, we will find the particular solution. The form of the particular solution depends on the form of the excitation signal. The forms of particular solutions corresponding to common excitation signals are shown in the table. From the table, we can see that the form of the particular solution is generally the same as that of the input signal. By substituting the particular solution and the excitation signal into the original differential equation, and solving for the undetermined coefficients in the particular solution, we obtain the particular solution. The general solution of the differential equation, i.e., the complete system response, consists of the homogeneous solution with undetermined coefficients and the determined particular solution. Using the known initial conditions, we can determine the undetermined coefficients in the homogeneous solution, thereby obtaining the complete solution of the differential equation. Now, let us illustrate the classical time domain analysis method with an example. In this example, we are given the differential equation of a certain second-order continuous time linear time invariant system, two initial conditions, and the form of the input signal. We are to find the complete system response. Step 1. Find the homogeneous solution. The homogeneous differential equation y sub h of t is y double prime of t plus 6 times y prime of t plus 8 times y of t equals 0. The characteristic equation is s squared plus 6 times s plus 8 equals 0. Solving the characteristic equation, we find the roots. s1 equals minus 2, s2 equals minus 4, which are two distinct real roots. Therefore, the homogeneous solution is y sub h of t equals k1 times e raised to the power of negative 2t plus k2 times e raised to the power of negative 4t. Step 2. Find the particular solution y sub p of t. From the form of the input signal f of t, we consult the table and assume the particular solution is y sub p of t equals k 3 times e raised to the power of negative t. Note: the form of the particular solution is generally the same as that of the input signal. Substituting the particular solution and the input signal f of t into the original differential equation, we solve for k3 equals 1/3. Thus, the particular solution is y sub p of t equals 1/3 times e raised to the power of negative t. Find the general solution. The general solution consists of the homogeneous solution and the particular solution. Substituting them yields the following expression. Using the initial conditions y of 0 plus equals 1 and y prime of 0 plus equals 2, We substitute into the general solution and its derivative to obtain two equations, from which K1 and K2 can be solved. Substituting yields the general solution of the differential equation. That is, the complete response of a system as follows. Now consider the following two questions. 1. If the initial conditions remain unchanged but the input signal changes, what will the complete system response, y of t, be? 2. If the input signal remains unchanged but the initial conditions change, what will the complete system response, y of t, be? Clearly, if the input signal, i.e., the excitation signal, changes, the complete response must be recomputed from scratch. Likewise, if the initial conditions change, the complete response must also be recomputed. The classical method of analyzing system response has the following limitations. If the excitation term on the right-hand side of the differential equation is complicated, it is difficult to handle. If the excitation signal changes, the entire solution must be recomputed. If the initial conditions change, the entire solution must be recomputed. The classical method is a purely mathematical approach and does not highlight the physical concepts of the system response. Finally, let us summarize the steps for solving a differential equation using the classical method. The general solution of the differential equation equals the homogeneous solution plus the particular solution. Find the homogeneous solution. From the characteristic equation of the homogeneous differential equation, solve for the characteristic roots. Based on the three possible cases for the roots, determine the form of the homogeneous solution. At this stage, the homogeneous solution contains undetermined coefficients. Find the particular solution. The particular solution has the same form as the input signal. Substituting the particular solution and the input signal into the original differential equation allows us to solve for the undetermined coefficients in the particular solution, thereby determining it. Determine the undetermined coefficients in the homogeneous solution using the known initial conditions of the system. Substitute the general solution into these conditions to determine the undetermined coefficients in the homogeneous solution. Finally, please complete the following exercises to consolidate the content of this lesson.